Okie dokie, off we go. I've lost count of how many sessions we've done, but I think this is only like the third low-level session of Legion School. And I guess we kind of started late, and I'm going to have to preface this with, if my other screen here starts flashing at me, I'm going to just stop in the middle, because high priority interrupts are high priority interrupts. But we'll charge ahead and assume that this machine won't crash on me while I'm looking at it, and do a round of Legion School. So the thinking today was to do, we did events last time. We talked about events and used that as a way to talk about active messages. So I'm thinking I'll spend today on the two other kinds of synchronization primitives that we have in the low-level runtime. So events are the kind of the baseline one of just the general way of talking about some event that's going to occur at some time, possibly in the past, possibly in the future, and using that as preconditions for other operations you want to perform, and how every operation gives you back an event that describes when it's going to be done. And so that's a simple thing when you know specifically one thing that you're waiting for, or a collection of things you're waiting for. Actually, I guess I didn't talk about collections of things when you want to wait for that, so maybe I'll do that one first. We'll talk about merging events. So let's go to low-level.h, where all these things are defined. And let me find class event. And so remember, this is they're different things that behave like events, but the event class is the part that handles waiting on things. Events get triggered in different ways, as we'll see, but the way you depend on them is uniform, regardless of what kind of event it is. So so we have has the event triggered? Do we want to wait on it? But then the other operation that we didn't talk about before is this idea of merging events. So if you have some operation that needs to wait until a collection of other events have occurred, each operation can only take one event as a precondition. So the way we do that is we let you merge multiple events into another event, and this other event has the property that will be considered to have triggered once all of its input events have triggered. Okay, and so there's two different ways that you can do this, depending on whether you have a static or dynamic list. And so we have two different implementations. One just takes between 2 and 6 arguments, and we'll merge them together and return a single event that describes when all those have occurred. And then we have the more dynamic one where you pass in a whole set of events, and we merge those together into one event. So let's go look at the implementation for this, because this will also kind of remind you how events work and show you some of the sorts of optimizations we do that make, among other things, profiling these things a real pain in the ass. So why did that not back up? That's having user interface issues. There we go. Okay, so we're back here. We're going to go look at lowlevel.cc, where, again, nearly all of the low-level runtime is implemented. And let's go find event, merge events. Okay, and so as with many things in the runtime, you see that the methods on the event handle are really just wrappers for passing it through to the actual implementation. And so we have as you'll see, we have a static method on genEventImpl that merges events for each of the kinds. So let's go find that now. genEventImpl merge events. Okay, so these two are very similar. Let's look at the set-based one, just because it doesn't have quite so much enumeration of things. And so let's look at all the different cases we deal with. And again, remember the model in the low-level runtime is when possible, look for the early outs to try to simplify things. And so we have a couple of those here. The first case is if you pass in an empty set of things to wait for, well, then kind of by definition, the degenerate case has already triggered. And so rather than even bothering to create an event, we get to use the special no event, which is the event that is by definition always triggered. And so we can return it whenever we want to say that you're not waiting for something, and without having to actually create an event object. So if you're didn't ask to wait for anything, well, then we go ahead and return no event right away. The next thing we do is we look through your set of events and see if any of them have obviously already triggered. And And so what we do, we set the wait count to 0, and we're going to basically iterate through our wait for list. And actually, so there's some fun optimizations here. And what we do is we ask, has the event triggered? If it has, we get to skip over it. If not, then we'll increment the count of how many things we're actually going to have to wait on. Basically, what we're trying to do here is we're trying to filter out events that have already triggered. So we'll run through the list, and we'll see events that are not known to have already triggered. Remember, has triggered is a conservative test. If it returns true, the event has definitely triggered, but it might return false even if the event is triggered and we just haven't heard about it yet. And so it's a very quick check, and so it can be used to throw out events that we know we don't need to bother merging in because they've already triggered. And so we're going to count how many there are here, and there's actually another optimization here, which is that there's actually kind of 3 interesting cases. The first interesting case is when every event in the list is already triggered, in which case you'll see again we don't bother creating an event. We'll just let's just look at that, right? If wait count is 0, so if every event in the list is already triggered, none we actually wait for, we again just return no event, because there's no point in creating an event that is already triggered. We just can use that one. The other fun case is when exactly one of the events in the wait for list is not known to have triggered. So n-1 of the events are known to have triggered. In that case, we again don't create another event. We just hand back the one that hasn't triggered yet, because the collection of them will trigger no sooner or no later than this last one will trigger. So we pass that through again, rather than creating another event to describe something that will behave just like this one. And then in the case where there actually are at least 2 events that aren't known to have triggered yet, we're going to have to create a little data structure to handle the merging. And so that's why if you go back up here to this test counting how many events have already triggered, as soon as we find 2 events that haven't triggered, as soon as the wait count reaches 2, we actually pop out of the list. We no longer have to test each one. We're going to have to build the actual list down below. So we look for the 3 early out cases of a completely empty list, or a list that has events where all the events have already triggered, or a list that has at most 1 event that hasn't already triggered, and all those things have relatively fast paths. And then if none of those have worked, then we're going to go ahead and actually create a new event that describes the merging of 2 or more other events. And so to do that, we're going to create a new generational event. And so merged events are just like any others in that we can reuse generational events as soon as the previous one is triggered. So this will either create a new event, or it will give us a new generation of a previously triggered generational event, and that will be our finish event. And then we're going to create an event merger object that uses this as the finish event. So this object will take care of counting how many of the input events have triggered, and when they've all triggered, it will manually trigger this finish event to describe the merge behavior. We will turn this generational event impl into an event handle that we can give back to other people. Since we can't give back the actual pointer to the internal data structure, we need a handle that we can send around between nodes. So we capture that in E. And then we now iterate over the wait for list again, and we do a bunch of logging somewhere in here. Okay, and then here's the key call, add event. So we're going to take every event from our list, and we're going to add it to this merger object. You'll see, we'll go look at the implementation, but there's a race condition between as we're adding these events, they may be triggering. And there's a race condition with, basically lifetimes of objects. And so as you'll see, we basically keep track of one more effectively event, which is are we done adding things to this merger? And we don't do that until we have added all the events. So that will avoid the race condition. And then we will return the event E. And so the reason we had to grab the handle here before we started adding these things is that, as we'll see, there's this race condition with trying to add events as they're triggering. And it could be the case that by the time we get out of this loop, everything we've added has already triggered. And therefore, once we say that we're done adding events, the merged event will immediately trigger. And so there are cases where this event that we hand back turns out to have already triggered. We don't do another test here because it's a race, and maybe it triggers right after we hand back the event. So you do have to be careful, though. It would not be safe, for example, to take the call current event on this finish event down here because if the event had already triggered, then somebody else may have called create gen event and already recycled this generational event for the next generation. And if we called current event then we'd be giving the wrong generation of the event and deadlocking. So it's very important with generational events that if you're going to ask for a handle, which remember captures the actual generation you want, you do that before anything that might cause the event to actually trigger. And so here's the model where we take the event, we do stuff that might cause it to trigger, and then we can hand back the handle. Okay, so let's go look at the implementation of add event. So this will be event merger add event. One of my other bad habits in this level.cc is for quite a few helper objects, I define methods in line, which has the annoying property of making it hard to search for them. Okay, so here's event merger, and here are all the method definitions in line. And so let's look at how the event merger works, right? So basically an event merger only has two things it needs to remember. It remembers the finish event that we're ultimately going to trigger. And it also remembers the count of how many input events we're waiting to trigger. And you'll see we initialize this count to 1 instead of 0. And that's to avoid the race condition of things triggering while we're adding. And so let's look at add event. That's fairly simple. We again have one of those early outs. If we're iterating over the list again, so if an event in the list is already known to have triggered, well, there's no point in adding it to our list because it's already triggered. If it hasn't already triggered, then we increment our count by 1. Note the use of an atomic here. And then we add ourselves, you'll see that every event merger is also an event waiter, which means we can add ourselves to events to be notified when they trigger. So we add ourselves to this event that we're waiting for, and so we'll get a callback on this object when this input event has triggered. So let's go see what happens. So here's the callback event triggered. The key to it right here is basically decrement the count. So we increment the count here for the number of input events we're waiting to see triggered. And here we'll decrement it, and we'll see how many are left. If we were the last decrement, then we will trigger the finish event. And so that's the key to it. Then there's a couple complications. Complication number 1 is that if we decrement it and we weren't the last one to decrement it, somebody else will be, and they may actually decrement it and delete this object before we're getting out of this method. So it turns out that although we're still in this method, the object may cease to exist after this decrement in an asynchronous way. And so that's why up here we cache both the ID and the generation of the finish event, because it would be unsafe to actually refer to this is really a this arrow finish event, and it would be unsafe to refer to that after this point. So we cache those here and use them down here. That's used both for the logging and for actually triggering the event. Actually, so this is the one special case here where if last trigger is asserted, then we're going to be the one who causes the deletion of the event. So it's actually still safe to refer to this finish event here. But if it's not, then we have to be careful. So that's why the logging uses patched values of ID and gen. And then if you remember from last time, this event triggered callback gets to return a Boolean that says whether the object, basically the this here should be deleted by the caller. And so this is how we manage the lifetime of these event merger objects, which is as soon as we've triggered the finish event, then we don't need this object anymore. And so if we trigger the finish event, we'll also return a true to the caller, and they will delete this object. And that's exactly why we can't refer to ID finish event after this point unless last trigger is also true. Okay, so we call add event on every event that's in our wait for set, increment our count, add it to the list. Each of those, some may happen right away, right? If the event triggers right away in a race, then the attempt to add a waiter actually will just has it call us event triggered right away. We know the count won't go down to 0 because we have this one extra count that we set up at the front, so the count can never go to 0 while we're doing these add events. And then if you remember from the caller, the last thing the merge events method does after calling all the add events is it calls arm. An arm is effectively just triggering the one more pseudo event that is known to happen after all the add events have occurred. And so we actually just do that by calling event triggered ourselves. In the race condition where all the events trigger before we get to the arm, this will actually return true because we'll be the last decrementer, in which case we actually pass that back out to the caller, and then the caller was going to delete the object right away if it turned out that we got an immediate trigger. So that's the basic idea. We build up a count of things. They can be triggering as we're incrementing the count, so we need to make sure the count never goes down to 0 until we're actually done. Once it does go down to 0, whoever calls event triggered, that is the one that brings the count down to 0 and causes the finish event to be triggered, will also handle the deletion of the object. So that's merging events. This gets used all over the place in the runtime, both internally for cases where I merge events, and also Mike uses it heavily in the high-level runtime to generate preconditions for high-level operations that have multiple actual preconditions. So any questions on merging of events? Okay, let me peek over at this other thing, and it hasn't crashed. Life is good. Okay, so now let's go look at reservations first, since they're not too weird from what people are used to. So let's come back up to low level H, and let's go find class reservation. So reservations are basically the Legion version of a mutex. And because we're a deferred execution model, they don't behave like normal mutexes. They're similar in that they have an acquire and a release. You can ask for a reservation, and later on you can release it. The thing is, the acquire doesn't block, and it always succeeds at some point in the future. So when you acquire a reservation, you immediately get an event back, and that event is the event that describes when you actually have the reservation. So instead of writing a critical section as acquire, do something, release, you generally write it as acquire, request some operation that is dependent on the acquire succeeding, then request a release that is dependent on the operation finishing, and then you go on and do the next thing. So unlike the traditional model of mutexes, where it's effectively the actual implementation of the critical section that wraps itself with a mutex, the normal model in Legion is actually the caller of the thing that needs mutual exclusion wraps the call in a mutex, and that lets it fit in the deferred execution model. Basically, you don't want a task to start consuming resources and then say, oh, now that I've locked down all these resources in this processor core, let me go wait on my turn. The idea instead is to wait on your turn first, and once you know it's your turn, then you can go start acquiring resources like a processor and memory and do your thing, and do it as quick as you can and release the event, release the reservation as soon as you can. So the basic model is you can create a reservation, you can destroy it, and then this acquire release model uses events to chain dependencies, right? And so you can see actually even just like everything else, even acquire can choose to wait on an event. And so this can happen for a number of reasons. One of the main ones is to avoid deadlock in cases where you need multiple reservations, right? The traditional way of not deadlocking when you have multiple locks in a system is to have some ordering of the locks, and everybody acquires them in the same order. And that way you know that you never get a deadlock where one thread is acquired A and needs B, and another is acquired B and needs A. Everybody has to acquire, if you're going to use A and B, you must acquire A before you acquire B. And so that's one reason why you might put a precondition on an acquire. You acquire A, and then you use A's event as the precondition for acquiring B. You use B's acquire event as the precondition for the actual operation you want to do, and then you can release both A and B contingent on that operation completing. And Mike uses this in the high-level runtime a bunch. And the nice thing about reservations is that they have nice proper orderings on them, so it's actually trivial to order them. We provide a globally consistent way of ordering the reservations, which makes sorting them relatively easy. So the other thing reservations can do, which shows up in a few places, although we're using this less and less, is that you can actually associate a small blob of data with a reservation. So when you create a reservation, you can specify a size of data, and then you can query the size of the data associated with it, and you can also get a pointer to the local copy of the data. And the idea here is, as we'll see, this data is basically, if you hold a reservation, then you always have a coherent copy of this data. And we use the reservations acquisition state to also control the coherence of the data, which makes it very easy to move small pieces of data around in a, think of it as a, cache coherent sort of way, but using the same messages that carry the reservation acquire release as well. So basically, if you want a reservation that is managing a small piece of shared state, this optimization here lets you basically have that shared state be moved around by the reservation rather than having to make it a separate operation of acquire the, in the traditional model, the mutex is just the mutex. So you acquire the mutex and then you go fetch the shared state. You do your thing, you put it back, and then you release the mutex. And in this case here, the data just moves around with the mutex because on these networks, moving a kilobyte or so is about as cheap as moving 8 bytes. So you might as well just move the data around with it. Okay, so that's what the reservation looks at like at the API level. Let's go look at the implementation in, as you might have guessed, low-level.cc. And again, user interface issues. Okay, low-level.cc. Okay, let's go find reservation impl. Okay, so here's all the methods on this. As you'll see, if you remember from 2 times ago, we had this dynamic table. Maybe that was 3 times ago, I can't remember. Dynamic table stuff that we use for all the mapping all the handles into objects. And that means that we have a free list that we have to declare. It also means we have this funny business where they get constructed ahead of time and then they have to be initialized. So the constructors tend to be boring, and then there's this init method that actually has the interesting stuff. In particular, it sets the baseline state where, as we'll see, the owner of a reservation can actually change over time. So the initial owner is set here. Initially, there's no locks on it, so the count is 0. It's not in use. And we'll see we have masks for keeping track of what other nodes are interested. And then if we create it with data, we'll allocate some local data for a local memory to hold that data. Let's scroll down a little bit and let's find a lock request. We'll do the local case first. Okay, here's acquire. So if I want to acquire a reservation, this is the path I'm going to go through. And again, this is the method on the impl, but the method on the actual reservation object basically just gets the impl and passes on the acquire request to that. So let's look at what we're going to do. So if you remember, actually, no, this one is split a different way. So I'm going to go look at reservation acquire first because there's a couple tricks with the way it's done that we need to talk about. Okay, so here's the actual entry point from the API. We're going to call acquire on a reservation. And remember, we might have an event that we're going to, as a precondition, and then we're going to need to return an event. So the first thing we're going to do in this is we're going to look at the precondition. Has it triggered? If it has, then we'll go ahead and do an acquire on the implementation. If it hasn't, then it's not safe to acquire it yet. And what we're actually going to do is we're going to package up this thing into a deferred lock request, which basically just is going to call this same kind of method after the wait on event has actually triggered. But there's a little bit of funny business also with the event that we return here. So this is one of the many operations in Legion that, if it doesn't happen right away, it needs to return an event saying it when it does happen. And so we need to create an event for that. So in the case where we're going to defer even the request, then we absolutely know the request isn't going to happen right away. And so this is where we go ahead and we create a generational event to describe when the lock has actually been acquired. And we'll return that. And then we need to remember that this is the event that we should trigger once we get the lock granted. If the acquire request is going to be made right away, then actually it turns out the event will be generated by the acquire call. And the reason why there's 2 different ways of doing it is that we're trying to actually optimize for the case where the lock can be granted right away. And as you'll see, we'll try to not create an event for that. So just like in the event merger, if I didn't have to create an event for something that was known to have happened right away, the same thing will happen here. Basically, if I can grant the lock right away, if I can grant the reservation right away, I'm actually going to return no event rather than creating an event, a generational event to describe something that I know has already occurred. So there's this funny business where the acquire method, in some cases, the after event has already been created here. So in the case where we're going to defer the request, but the request will be granted right away, you still need an event because we didn't know the request was going to be granted right away yet. And so we create that here so we can return it right away. But if we're going to make the acquire request right away, then we will allow for the optimization where we can actually return a no event. So I don't know if that made any sense, but you'll see in here in the actual implementation of acquire how those 2 different cases happen. So the implementation here does not take the precondition, because you saw we handled the precondition if there was any in the wrapper call. But it does take this after lock. So basically, if the precondition had to already create the finish event for the acquisition, it will pass that in. But in the case where we didn't have a precondition, then we'll optimistically pass in a null. Basically, we won't create the generational event until we need to, so we'll pass in a null here. And so that's the first thing we do. We say, well, was an event already created? If so, that's the handle we'll return. We have to return that handle because we already decide that's the handle that's going to track it. If not, we'll optimistically assume that that we can use no event to indicate immediate grant of the reservation. So we'll do that first, and as you'll see, if we can't immediately grant it, then we'll turn this into a real event below. We'll do some logging. Reservations have two different ways you can acquire them. You can either ask for exclusive access to a reservation, think of that as a writer lock, or you can ask for shared access and think of that as a reader lock, although it's a little bit more general in that you can have different classes of readers that don't get along. And so the model is basically there's, we present it as 2 different things, a mode number and exclusivity. But in reality, what we do in the hardware is that you can have in the implementation, you can have no more than, two requesters can share a lock if they have the same mode, as long as that mode is non-zero. The mode equals 0 is special, and only one requester can hold a lock in mode 0. And so what we do is actually, if although we show it externally as a mode value and a Boolean, basically if you ask for exclusive access, we just map you onto mode 0. That's what mode exclusive is here. And then we throw away this exclusive flag. We do it entirely based on the mode. So that collapses those. The default is that we're not going to get the lock. And we're also going to have to keep track of whether we need to request the lock from some other node. So once we've set up some things, we go take the mutex, low-level mutex on this data structure. And let's ignore the special cases. If we're the owner of the lock, then we have all the information. We can decide what to do. In the first case, the lock is not currently held, so the count is 0. Or the mode we're asking for is compatible with the current mode of the lock. And in either of those cases, we can immediately grant the lock. We can immediately grant the reservation, so we increment the count. We set that we got the lock. And once we fall out of this section holding the mutex, we'll notify people. So this is the fast case where we can grant the lock right away. If that fails, then we can't grant the lock right away. And so we need to figure out what we're going to do about it. There's a couple different cases here. Wait, why is this path here? I think this piece right here might be dead code. This is, again, checking to see if we can share. This is count equal greater than 0, but the mode is match, which is actually the same test as right here. I think this is actually dead code, and so we'll ignore it. But the other case is that, so if both of these tests fail, then that means that the count isn't 0, and the mode we want is incompatible with the mode that it's currently in, which either means that they're different or we're both mode 0, in which case we're always incompatible. And so we'll go down here and we'll basically, oh, I see, I'm in the wrong if here.
You notice there are separate if-else blocks there, right?
Yeah, I miscounted my braces. Okay, never mind. So let me back up a little bit. In this case here, the simple test was if we're the owner, then if we're the current owner of the lock, then we get to decide who's the next owner. And if that's us, then that's great. Otherwise, you'll see we deal with it down below. This whole branch here is actually the case where we are not this node is not the owner of the lock. And so there's two cases here, which is we may not be the owner, but we may already be sharing the lock, in which case we can add additional sharers and grant right away. Or we don't own the lock, we don't have even a share of the lock, and we're going to have to go request it. And so what we're going to do here is we're going to build up the information we need to go send a message to the actual owner of the node saying that we would like to request this lock. We don't actually send the message here because we're holding the mutex, and we'd like to not be holding mutexes when we send active messages. So we remember that we're going to request it, but we don't actually request it till below. The last thing we have to do while we're holding the mutex is if we didn't get the lock, and if we didn't already create an event to describe when the lock will be granted, we go ahead and create that event now. Because it's not going to happen now, it's going to happen in the future. We need an event to describe it. And we're going to put our, we're going to remember that this is one of the requesters to the lock. So it turns out that we don't create any extra data structures to remember who's waiting on locks. The list of people waiting on locks is exactly just the finish events that we trigger one at a time when we grant locks, when we grant reservations. We do remember we do sort them by which mode they're asking for, but we stick that lock on the local waiter list, and we'll pull it off and trigger it later on. So either we set got lock to true here because we are able to either give ownership of it or share existing ownership of it, or we put ourselves on the list here as a local waiter. This curly brace, if I have the curly braces right, is the one that lets go of the mutex on the internal data structure. So now we can start, oh, no, I lost again. This curly brace here is the one that lets go of the mutex. So now we can start doing things like sending active messages. So in particular, if we decided that the lock was owned by another node and we wanted ownership of it, this is where we send a message to the other node asking for the lock. We built up the arguments we need up here, but here's where we actually send the message. And then the other case you have to deal with is where we did get the lock, but we had already created an event to describe when the lock was going to be granted, perhaps because we were deferring the request, in which case it's up to us to make sure we triggered the lock. In either case, we return the event that will describe when the lock has been granted, which may be right away if this path happened, or this may be a no event if we fall through the quick case of a non-deferred lock reservation request that is granted, and or it may be an event that hasn't occurred yet because we're still asking for the lock. Okay, so if the event hasn't triggered by this time, there's two possibilities. Either we're the current owner of the lock, and just there's some other operation on this node that is currently using the lock, in which case we put ourselves on this local waiter list but didn't send any messages. Or we aren't even the owner of the lock, and we put ourselves on our local waiter list and sent a message to the node that is the owner saying that this current node would like to own the lock at some point. So we can look at that goes through two different paths. Let's look at the case of where we are the owner and eventually somebody releases it. So let's go find release down here. So this gets called by a node once it has been given the reservation and done whatever it wants to do. At some point, it'll call release on it. And so we're going to have to do a couple things here. We're going to When we release a reservation, one or both of two things can happen. One is that there might be local nodes, local waiters on this node that were waiting on the reservation, and that we can grant them the reservation and wake them up. And we may also need to transfer ownership of the lock to some other node. And actually, maybe those two are exclusive. We'll see. I've changed things around. So the first thing we'll do is we'll go inside this block here, and we take the mutex, because now we're going to mess with the internal data structure. And the first sanity check we're going to do is we're going to assert that there's actually at least one lock held on this, that we're not getting a false release. And one thing that's funny here is that I'm not testing against 0. I'm testing against this constant called 0 count. I can't remember what the particular bug was that made me do this, but basically, an actual value of 0 in this count field is illegal. Is illegal. There's some offset that's unlikely to be accidentally guessed number. There was some data clobbering going on, and 0 was the case.
It was the case where we were having the end of the buffers not show up in the active messages.
Oh, it was that one?
Because of, yeah. And so you were putting in the special counts, and it was because we were not properly waiting for the whole active message to be in the buffer before we handled it.
Well, there was also the one where GasNet was screwing things up for us. In any case, so this is a bit of defensive programming where a value of 0 in memory is actually illegal, and this lock is not held state is count equal to this 0 count constant, which is interestingly non-zero. So we assert that actually there are actual counts, actual locks held, and we'll decrement it since we're releasing one reservation here. If that decrement doesn't cause the count to get to the 0 count, well, then this is a shared lock. And so there's still sharers available, and although this particular user of it has released it, other people haven't, and so we can't actually give this lock to anybody else. And so we break out of this loop. That's why this is a do while false rather than just the normal scoped block. But if we get past this break here, then it means that we're done with the lock and it's time to give it to somebody else. So there's a couple different cases here. One of them is that we didn't own the lock. And so if you don't own the lock and you had a share of it, then it can only be in a shared mode. So we sanity check that this wasn't an exclusive lock. And we'll send a message to the owner of the node that owns the lock saying this node no longer wants a share of the lock. And so that will be a message, but then we don't have to track anything else because we don't own the actual state of the reservation. The other case is that we are the owner. And now we can do a couple things. We can see if there are any local waiters to wake up. And so that's what we do here. Basically, this is a little helper function that's just going to look through our waiters and decide, is there anybody locally that wants a lock? And for folks that have read our papers or listened to our talks, reservations are massively unfair in Realm. If there are any local waiters, they always, always, always win. We will never transfer a lock to another node if there are any local waiters. And that's intentional because transferring a lock between nodes is much, much more expensive than transferring a lock with a reservation within a node. So basically, we'd like to exhaust all the local waiters before we transfer it to another node. And there's an assumption here that basically you can't get an infinite supply of local waiters that would starve the other nodes. And you can certainly write code that violates this assumption, but the normal use model in Legion is such that eventually, our approach is that we're at least making forward progress, and we'd like to make forward progress as fast as we can. And if at some point you stop making forward progress, well, then it means there aren't any local waiters, and you can give the lock to somebody else. So you can certainly come up with cases where that's not the optimal scheduling decision, but there are enough cases where it is. That's the mode we operate in right now. So if there are any local waiters, we put them in this to-wake list, and we get a true value back here. And another sanity check that basically we shouldn't say there are local waiters and not pick one to wake up. That would be a deadlock. If there aren't any local waiters and The remote waiter mask is non-empty. This is a stylistic thing. Mike is using operator bang for emptiness, and so you have to use operator bang and then negate that, which is why there's two bangs here. Mike will note that I actually have that fixed in the in the latest version. I have an empty method, so I can remember what double bang actually means. But in any case, if there are remote waiters, then we ask the mask for who's the first guy who wants it. And we basically we're going to give it to the first guy that wants it. And so we take that out of the current remote waiter mask. And what we're going to do is we're going to send a message to that node that makes them the owner, and then they can decide what to do about things. In particular, we're going to send to them a list of any other nodes that we're waiting on it. And it will be their job to further grant things. But basically, we're going to pick the first guy who's not set, the first guy who's the first remote node that we know of that's waiting. We're going to give the lock to him, and then he's going to deal with it. This code here is also unfair in a way that's less good. It hasn't burned us yet. But basically, lower numbered nodes are effectively given preference over higher numbered nodes. And that's probably not the right thing. Probably once you send, if you're going to transfer a node, a reservation between nodes, you should probably be round robining. And so on my background list of things that I always say I want to do and forget about is that this should probably be find the first guy set, larger than my current node ID, wrapping around as necessary. So that if you have lots and lots and lots of contention for a reservation, then it should round robin between the nodes, letting each node basically exhaust all its local waiters before passing it on. And so, yeah, I should probably fix that at some point. But fundamentally, the idea here is pick some other node that's going to own it and give them the lock and make it their problem. And as part of making it their problem, you also have to make sure you let them know of the n-1 other waiters that you were keeping track of. So this do while loop was just so that we could have that break there in the middle. But either we will decide to have released our share of a lock to the original owner, or we'll have picked local waiters to wake up, or we will have decided to transfer the lock to somebody else, or if there was nobody at all waiting for it, then basically the count goes to 0 and nothing else happens. And if you remember, that was the fast case we had before, where if the count was 0 and we owned the lock, then we were able to do immediate grants. But so now we let go of the mutex, and if we're releasing a share of the lock, send that message. If we are granting ownership of the reservation to another node, send that message, and note the little bit in here about where this is where we tack on a copy of the local data. So if as ownership of reservation transfers between nodes, we ship that around as part of the lock grant message. That's cheaper than doing it as separate messages. And then once we send whatever messages we're going to send, now if we have any local waiters, we will trigger those events. And remember, like I said, local waiters are remembered just in terms of the finish event. There is no other metadata for it. So we just take whatever finish event, whatever grants we're going to grant, and trigger those events, and then we're done. So that is releasing a reservation, right? So if you release a reservation, either nothing happens because there's still local sharers, or if we were the last of a sharing of a remote reservation, then we'll release it. If we were the owner, then we will either grant it to one or more local waiters, or to at most one remote node. Or in the case where nobody wanted it, then it just sits here in an unclaimed state till somebody else tries to acquire it. Okay, let's see. Let's look at the lock request message now. So we did all the stuff that happens on one node, and so the last thing we need to worry about is what are the active messages that get sent around. And there are 3 different kinds of messages that can be sent. There are requests for locks, there's releases of locks, and there's grants of locks. So let's look first at the lock request. And you'll note that the implementation here is a little bit schizophrenic as to whether we call them locks or reservations. And I'm very schizophrenic when I talk about it. The external name is reservation because it confuses the heck out of people talking about them as deferred locks outside. Inside the implementation, we tend to call them locks still because that's easier to type than reservation. Okay, lock request message. Okay, so here's a lock wait, what the heck? No, okay, yeah. So here's a standard active message setup. As you recall, we need a structure that defines the arguments that are carried in a lock request message. We need a method, a function that's going to handle the receipt of a lock request message. Then we have this wacky type def that wraps all these things up in GasNet active message foo. But so when you want to request a lock, the interesting things are which node is doing the requesting, which reservation are they requesting, and what mode are they in. And remember, this is the case where mode 0 means exclusive, mode non-zero means an attempt to access get shared ownership of a lock. So let's go look at handle lock request. This is a case where, unlike before, the acquire method was handling cases of local requests for a lock, and so individual operations requesting access to a lock. For these messages, we clump things by node. So remote requests are done on a per node basis on behalf of one or more local operations on that node that want it. So we do things at the node level here. Let's look at what happens. A little bit of logging again, and then the same model. We're going to take the mutex, we're going to do stuff, but we're not going to send any messages while we're holding the mutex for the data structure. So we need to remember what messages to send and send them afterwards. So a couple different cases to worry about here. The first case is where we get a request from somebody for a lock that we don't even own anymore. So the data structure we have here remembers who we think the owner is, but that owner may have already given the lock to somebody else, and we don't broadcast that information. We determine it lazily. So basically, if node A thinks that node B is the owner, it will send to node B the request for that lock. And if node B has already given the ownership of the lock to node C, then what node B will do is simply forward the request on to node C. We don't even bother sending node A information about this information, about the forwarding to node C, because node A remembers that it has already sent a request, so it will not send any more requests for this lock until it eventually gets it granted. So there's no point in telling it to send further requests to node C because it's not going to send any further requests. Node A isn't going to send any more requests for this reservation until somebody actually grants it. So as long as we forward node A's request for the reservation on to node C, that's good enough. So we will remember that we need to forward the request to the actual current owner, or at least who we think the current owner is, which also may be stale. And then we'll hop out of here and we'll send the request out. And so you can get this funny behavior where if you've got a lock that's moving around the system, you can have requests all chasing this lock around the system, but it can't happen forever. Basically, any given request can only be forwarded n-1 times, because eventually it's going to get to the actual owner. Actually, let me take that back. A given request can actually be forwarded arbitrarily many times. However, the amortized number of times that a given request can be forwarded is bounded. And so again, we have this forward progress property that somebody is always making forward progress. Whenever we transfer a lock, forward progress gets made. There may be other requests that are chasing behind it for each of the nodes that doesn't currently own the lock, but each of them only sends one request until they finally get it. And a transfer results in at least one person being happy. So you can show that there are pathological cases where every request gets sent n times, but forward progress is still made. There may be one guy who just gets really unlucky and keeps losing out, but somebody's always getting lucky. And we do this rather than having global communication as to where things are, just because you end up with a super linear number of messages, and we're worried about scalability in that case. So since the average number of messages is order n, if there are n requesters, this is what we like. And I am just about out of time, so let me zip through this, and then we'll do something else next time. Okay, so this was the case where we didn't own the lock. So the rest of this is where we are the owner of the lock, so we get to decide what to do about it. If the current count is 0, so basically if the lock is on this node but nobody currently wants it, and we're not sharing it with anybody, well, then we're allowed to transfer the lock to the person that requested it. So we will grant, we will decide that we're going to grant the reservation request to the other node, and we will set up the information we need here. Later on, we'll send the message down here. This code here is actually, I think, basically just a copy and paste, that we're going to send a copy of our remote waiter mask. But I think you could show that basically to hit this code here means this waiter mask must be empty, because if the waiter mask wasn't empty, we would have already transferred the lock to somebody else. So actually, I'll probably go in and replace this with an assert that there are no remote waiters, just for sanity. But basically, we're transferring the lock, so we transfer everything. And as you'll see down below, we also transfer the data. Case 3 is we're the owner, but we're not going to grant the lock right away. Either it's because we've got some local user that hasn't let go of it yet, or the other case is that we don't have any local users yet, but if we granted shared ownership of the reservation to other nodes, we can't give away the lock until those shares are given back. So either way, we're not going to send a message now. What we're going to do is we're going to set the bit corresponding to the node that made the request in our remote waiter mask, so that we know that when the lock does reach an uncontested state, that this is one of the nodes we would consider forwarding it to or granting it to in the code we were looking at before. So those are all the cases. We hop out of here. If we decide we're going to forward the request, we do it here. If we decide we're going to grant the request, we do it here. And that's pretty much it. Okay, I am over time. My other thing still hasn't crashed, which is good because I wasn't paying attention to it for half an hour. Before we stop the recording, are there any questions people want to ask about locks? I didn't get to barriers. We'll do barriers next low-level time, and Mike and I will figure out when that is. Okay, well, I guess we're done for today. Have a good rest of the week, everyone, and we'll see you next week.